Okay, so hi, I'm here today to talk about integrating a solid hemisphere with a constant density throughout and integrating this to find the center of mass. So the first thing we'll do here is look at how this is represented on the z, x, and y axis with the circle in the xy plane, and that's just a uniform circle with a uniform radius. So then we look at the other half of the hemisphere, this half circle rising up into the z, and we see that in x and y that changes uniformly. So we can safely assume that because of symmetry, we are really only integrating this center of mass in the z direction, because it is the only thing that's really changing. So when we look at that, we can say, okay, well, we know z in Cartesian coordinates equals r cosine theta, and we're getting that from this angle right here. You can see this angle labeled theta, where this azimuthal is here, and it's phi coming from the z axis. So we go over here to our integration, and it's important to point out that the center of mass integration is 1 over mass times this guy here, which is what we're using for density, which is mass over area. And then this will be a triple integral in spherical polar coordinates because we have a half sphere. So it feels like the right path to take. And so we'll use the small changes in volume given to us here, which is r squared dr sine theta d phi, which is also a mouthful. So in doing this integral, we set it up here, and then we evaluate one integral at a time, depending on the bounds of integration and how they relate to our different variables in our equation. So first, we will integrate r cubed with respect to dr. And that, of course, is going to give us r to the fourth over 4. And here, I'm just going to go ahead and make this move to simplify my writing, where I'm going to take this whole thing and call it equal to the constant k. So moving down here, we show constant k here. And we have our second integration, which is cosine theta sine theta d theta. So we see here that cosine and sine theta, you can't just solve that integral in this state. So we'll use a u substitution here, where we will take our sine and call it u, and sine, obviously, its derivative is cosine. So when I rearrange my d theta for du, I have this cosine term in the denominator to cancel this other cosine term, and we're left with the simple integral u du, which of course is u squared over 2. However, we know that that u is sine, so moving over here, we see a little side work where I have sine of pi over 2 squared over 2 minus sine of 0 squared over 2. And sine of pi over 2 becomes 1 squared, still 1, and sine of 0 is nothing. Well, it's 0. So we see that this really just evaluates down to 1/2, and we'll bring that 1/2 over here and multiply it by k, and then again we're left with a very simple integral, which is just 0 to 2 pi d phi. So the integral here, of course, is phi, and phi is going to be evaluated from 0 to 2 pi, so really we're just going to get a 2 pi term from that. And then we can come down here and unpack our k, we'll unpack our density, and we see that we'll cancel masses, r cubed, pi, and this whole thing will turn out to be 3/8 of the radius. So about 3/8 of the radius up in the z. Looks maybe marginally right here. So that is our center of mass in spherical polar coordinates. for a half solid hemisphere with uniform density.